The next theorem guides us how we can improve the unbiased estimator. To see when an unbiased estimator is the best unbiased estimator, one could ask that how we can improve the given unbiased estimator. The procedure is very simple and straightforward. We assume that W is an estimator which satisfies that expected value of W, that is G of theta, which means that it is an unbiased estimator. And we have another estimator which is denoted by U, and the expected value of U is equal to 0 for all theta. U is an unbiased estimator of 0. Note that the unbiased estimator of 0 is nothing, that is just as a random noise, and it means that there is no information in the estimator of 0. So for this we state a theorem, that is theorem 7.3.20 in Cosell and Burgess book. The statement of that theorem, that is, if expected value of W, that is G of theta, and W is the best unbiased estimator of G of theta, if and only if W is uncorrelated with all unbiased estimator of 0. So actually U, we assume another estimator, and we assume that it is an unbiased estimator of 0, and we are going to compare that W and U, and we see that W is the best unbiased estimator among all other estimators. So how we are going to prove this one? Using the above argument, if W is the best unbiased then it must satisfy that covariance with respect to theta of W and U is equal to 0, which means they are uncorrelated for all theta and for any U, satisfying that expected value of U, that is equal to 0. So the necessary condition which we want to show that the covariance of W and U, that is equal to 0, is going to fulfill. So the necessary condition is satisfied. For the sufficient condition, suppose we have an unbiased estimator that is W, which is uncorrelated with all unbiased estimators of 0. Let we define another estimator. Let W dash be any other estimator such that obviously it is also unbiased estimator, so the expected value of W dash, that is actually equal to the expected value of W, and that is equal to G of theta. Now we will show that W is the better than W dash. So we write W dash as W dash is equal to W plus W dash minus W. So we just only add and subtract W from W dash. Now taking the variance on both sides, we get that is variance of W dash. That is actually the variance of W plus the variance of W dash minus W plus 2 covariance of W and W dash minus W. So this can be written as variance of W plus variance of W dash minus W. The last component vanishes because W dash minus W is an unbiased estimator of 0 and is uncorrelated with W that we have assumed already in the theorem. So this factor is going to 0, so it is going to vanish. Also this factor, also the variance of W dash minus W is greater than or equal to 0, and it implies that if that is greater than or equal to 0, so the variance of W dash is greater than or equal to the variance of W. Since W dash is an arbitrary, so it follows that W is the best unbiased estimator of G of theta. So because that is an arbitrary estimator, so it is greater than the variance of W dash is greater than the variance of W. So it is an arbitrary, so it follows that this our original estimator has a smaller variance. So if it is a smaller variance and it is already unbiased, so it is the best unbiased estimator of the theta.